Thank you, Greg. For the pure biologists in attendance, because my talk is called Writing about Quantum Mechanics for Biologists in part, this presentation presupposes no knowledge of physics nor biology. And since it is entertainment and not a set of experimental results, I ask that the physicists and biohybrids kindly hold questions until the story is told. First, I'm going to talk about the fundamentals of the many worlds theory. Then we will explore the life of the strange man who invented it. And as a special treat, we will hear from the theorist himself, despite the fact that he is dead. In the fall of 1954, a graduate student in physics at Princeton University began writing down the formal argument for one of the strangest and most controversial theories in the history of modern physics. The young man was Hugh Everett III, a talented mathematician and game theorist. He initially called his theory wave mechanics without probability, but soon, for political reasons, he renamed it the relative state formulation of quantum mechanics. It is known now as the many worlds interpretation of quantum mechanics, although until the end of his days, Everett preferred to call it the theory of the universal wave function. Combining information theory and quantum mechanics, Everett proposed a solution to an infamous paradox in science, the measurement problem, a problem which has been with us since the advent of quantum theory in the early 20th century. Simply put, the measurement problem arises because an atomic particle can move through space and time in a multiplicity of directions at once, as if it is an expanding spherical probability wave simultaneously passing through all possible trajectories in a coordinate space of infinite dimensionality. But obviously, when we interact with the particle, when we measure it, we always find it at one place and time, not at many places and times. This fact of obtaining a single measurement result, this common sense experience, does not seem to accord with the fundamental rule of quantum mechanics, the time-dependent Schrodinger equation, a wave function that evolves each state of a quantum system forward in time linearly. As this linear evolution is quite literal, collections of atomic particles, basketballs for example, can exist in a superposition of quantum states that continuously evolve through space and time, exploring every physically possible configuration for each state. A superposition can be depicted as a wave which can be decomposed into its constituent parts, which are also waves. Quantum mechanical waves, like all waves, can interfere with each other and change size and shape as peaks add to peaks and troughs to troughs and peaks cancel each other. The quantum wave equation encodes all of the elements of a superposition, all of the physically possible positions, energy levels, momentums, and other properties that a microscopic quantum particle or collection of what we call correlated or entangled particles can assume in a coordinate system of infinite dimensions. And it can do this over superluminally separated distances between galaxies, and according to Everett, between universes. Experimentally, we discover the components of a superposition by repeatedly making measurements of the same quantum system. Well, it's not exactly the same system, but since each repeated measurement is experimentally prepared under the same conditions, collecting these measurement results is tantamount to recording many measurements of a single property of a single system. And when we repeat these measurement procedures hundreds or thousands or millions of times on identically prepared systems using cloud chambers or linear accelerators that detect wavy interference effects, we find that a particle can simultaneously inhabit a number of different positions, energy levels, momentums, and spins. The wave function describing a superposition circumscribes the probabilistic range of each of these elements. It precisely displays the linearly evolving changes in these properties without losing track of multiple interlacing threads of cause and effect. In fact, the ability to calculate quantum mechanical probabilities allows us to design machines ranging in complexity and power from simple transistors to nuclear reactors. But nature does not require human agency to participate as it evolves each property of a quantum system through space and time. Nature does this automatically, as if each property, each particular position, energy level, or spin follows a causally unique trajectory. And each of the superposed elements in such a deterministically evolving quantum mechanical state can be described with a wave function. And all of the wave functions of all of the elements in a superposition can be combined to describe the entire system as a synergistic whole that can generally be decomposed into subsystems, including the single isolated subsystems that we, the makers of quantum measurements, record, one measurement at a time, until we build up a collection of measurements, a distribution of relative frequencies of events that allows us to describe the totality of all physically possible events occurring in a quantum superposition with a wave equation. Here's a depiction of a very abstract wave function by an artist named Warren Bellow, who told me that he was inspired to throw paint at the canvas after reading my biography of Everett. Back to Schrodinger's wave equation, invented in 1926. It employs complex numbers that use I, the imaginary number, or the square root of -1, to evolve the components of quantum systems through the paces which nature dictates, regardless, of course, of whether or not there are painters named Warren Bellow around to witness such changes. Good. The next piece of the puzzle is called the Byrne rule. The Byrne rule is named after its discoverer, Max Born. It's a simple formula used to extract probabilities in quantum mechanics. The rule tells us to square the complex number associated with each component of the quantum state, as encoded in a wave function, in order to arrive at the classical probability that a particular element of a superposition will appear to us in our macro world at position x or position y at time t or time v, at momentum p or q, or z spin up or z spin down. For example, an electron may be reliably predicted to pop up at position x 54% of the time and position y 46% of the time. But we never know at which position it will be recorded after any given measurement interaction. Only the probability that it will be at x or y, and the record of these results is called a probability distribution. And the rules governing quantum probabilities also tell us that the probabilities for the object to appear at position x or y, as extracted from the wave function by the Byrne rule, will always add up to 100%, or one unity, even if the number of possible positions or energy levels or momentums approaches infinity. But useful as these two formulas are for calculating to an incredibly accurate degree the chance that an atomic particle will appear at position x or position y, they do not tell us why they work to do so. They are ontologically mum. They reveal with extreme precision the probability that a singular result will reoccur, but they do not tell us why we experience only one measurement result at a time instead of sensing all the results at once. And this is a problem, not for the universe, but for us. Wrong von Neumann. In the 1930s, Paul Dirac and John von Neumann recognized that even though the Byrne rule works, they could not derive it from first principles. So they were compelled to postulate it as an axiom because they could not explain why one result emerges from the wave function containing many possible results when the experimenter measures or interacts with a quantum system. And this axiom became known as the collapse of the wave function. What does that mean, collapse? Graphically, picture an atom, or in this case a collection of atoms, as a probability wave composed of many smaller waves, some of which bear positive numbers, the peaks, and some of which bear negative numbers, the troughs. And each wave represents a physically possible position in space for the atom. Now, combine all of the wavy peaks and troughs into a large wave, which is a superposition of the smaller waves. It encodes all of the physically possible positions of the atomic system, given the quantum geography of its environment. Now, picture this wave as stretching from a laboratory on Earth to Alpha Centauri. After a macroscopic measurement device interacts with the atomic system, the abstract wave function, describing all of its possible positions, instantaneously and inexplicably collapses from a superluminally sized tsunami of a wave into a needle point locating the atomic object inside a scanning tunneling microscope with probability 1 at time t, even though a subsequent measure could still locate it at near Alpha Centauri. Everett regarded the wave collapse idea as nonsensical, as did Erwin Schrodinger and and as did, to a certain degree, Niels Bohr, both founders of quantum mechanics. In the 1930s, Bohr developed a philosophical approach toward the various paradoxes posed by quantum mechanical experiments, of which the measurement problem is but one. He called his overarching solution complementarity, but it is popularly known as the Copenhagen Interpretation. The immensely influential Bohr declared that we can never know what goes on inside the quantum realm, and that quantum mechanics can only be described linguistically with terms conformable to classical or non-quantum physics. And most importantly, that measurement devices and observers are not part of the quantum mechanical systems with which they interact, even though they themselves are composed of atomic particles. Observers must remain external to the indeterministic systems which they measure, said Bohr. Everett labeled Bohr's approach, quote, a philosophical monstrosity with a reality concept for the macroscopic world and denial of the same for the macrocosm, end quote. Observers are part of the quantum systems with which they interact, Everett insisted. The constantly evolving wave function fully describes the particle and the instrument that measures it, and the scientist who observes and records that measurement, and the lab assistant who observes her, and so on and so on. The universe, said Everett, is not artificially divided between the quantum and the classical realms. It is completely quantum. And the wave function is, quote, real, end quote. According to Everett, there is no such thing as wave function collapse, but only the illusion of wave function collapse. Illusionary, since each observer is stuck on a causally consistent trajectory somehow picked out of a multiplicity of physically possible quantum mechanical histories. And furthermore, Everett insisted, quantum mechanics is not indeterminist. It is deterministic. Reality is encoded in a universal wave function, which can, in theory, describe all of the possible positions, energy levels, momentum spins, and cross-referencing correlations of every particle that ever was or ever will be. In other words, every quantum subsystem, every piece of a wave function is shaped relative to the quantum state of sister subsystems with which it is entangled in a network of infinitely branching universes, which in sum instantiate every physically possible event. And for that matter, embrace regimes in which the laws of nature as we know them no longer apply. There is, in other words, a global superposition describing a universe of universes, a universal wave function. And while Everett's logic is considered by many prominent physicists to be reasonable, the ontological consequences of the theory appear to be absurd, except to science fiction writers who instantly fell in love with Everett and his multiple universes, and to cosmologists who delight in calling his system of entangled macrostates a multiverse, or even a landscape of possible worlds or vacuum energies. But because Everett's theory makes the same predictions that the wave function collapse models make, his interpretation is subject to interpretation. One way of understanding the theory is in terms of physically splitting subsystems inside a distribution of universes. Everett showed us that it is mathematically consistent to say that when a scientist measures or interacts with a superposed atomic object, he in effect splits into numerous copies of himself, each copy correlated to a single element in the measure's superposition. After a measurement, each copy of the observer inside the global superposition described by the universe related to, entangled with, a particular quantum object in the set of all physically possible positions of the object observed. And each copy of the observer records the object in a different position and bearing a different probability weight according to the Byrne rule. And to the extent that the very notion of probability can survive this theoretical exercise, the probability distribution associated with the sum of these observations is unity. As Everett diagrammed in this page of his handwritten draft thesis, wave functions do not collapse, rather they evolve and continuously branch as new correlations emerge inside the quantum substrate. And each universe in the quantum multiverse is constantly branching into separate but parallel worlds that cannot communicate with each other in a classically describable sense. In Everett's model, each parallel universe self-records a consistent history of correlated events drawn from a range of physically possible histories. And no one of these histories is any more or less real than another, Everett insisted. They are all equally real. Importantly, this does not mean that anything is possible. Physical reality constrains what is probable. But you may ask, and you are right to ask, how can there be such a thing as probability if every physically possible event occurs? Aha, said Everett. Probability is also an illusion brought about by our inability to access all of the information encoded in the universal wave function. The Byrne rule works, he said, because a typical branch, as experienced by a typical copy of a typical scientist, will contain measurement records that satisfy the usual quantum statistics. And so far as Everett was concerned, his theory was empirically faithful. He did not require that his mathematical formulation provide empirical proof of the existence of parallel worlds. It was enough for him that it was consistent with the evidence that there exists a single world in which there is more than one observer, our world. According to physicist Bryce DeWitt, writing for Physics Today in 1970, Everett showed that, quote, this universe is constantly splitting into a stupendous number of branches, all resulting from the measurement-like interactions between its myriad of components. Moreover, every quantum transition taking place on every star, in every galaxy, in every remote corner of the universe is splitting our local world on Earth into myriads of copies of itself. Here is schizophrenia with a vengeance. He later retracted that statement. A consequence of DeWitt's interpretation of Everett is that there are universes in which dinosaurs survived and humans remain shrew-like, universes in which Lars Bildstein wins the California and New York state lotteries every single week, universes in which Wall Street does not exist and global resources are equally shared. Sure, it seems like an improbable idea, but in one form or another, the many worlds theory is recognized as a contender for interpreting how quantum mechanics shapes physical reality. In fact, so seriously is this fantastic idea taken that there is a school of Everettian philosophy at University of Oxford. And if you look at the index of just about any book on the foundations of quantum mechanics, you will see the entry Everett, Hugh, 3. Everett's conception of a universal wave function is said to be useful to theoretical physicists and cosmologists who treat reality as wholly quantum, as they explore the cosmos from inside the cosmos, as opposed to trying to describe it from outside the cosmos, which is impossible. In July 2007, Nature featured his theory on a cover celebrating the half-centenary of its publication. And the BBC and Nova and National Geographic Channel have produced films explaining his theory to the degree it can be explained. This presentation, by the way, will continue to be cat-free, if you know what I mean. Today there are various interpretations of Everett's interpretation, some of which applaud his model of pure wave mechanics without collapse as logical, but do not demand that the branching universes be ontologically real. And there are other ways of dealing with das Messproblem, as the Germans call it, such as hidden variable theories or Jim Hartl's consistent histories model. But interpretive preferences aside, the argument substantiating Everett's model multiverse is thought by many to be relevant to formulating a theory of quantum gravity. Starting in 1970 with the work of Dieter Zeh at the University of Heidelberg, certain problems with Everett's model were addressed, and some say solved, by the application of quantum decoherence to the theory. The decoherence phenomena arises from quantum systems entangling with their environments and decohering or dynamically uncoupling from coherent superpositions of states into classically delineated histories. Zeh was soon joined by Wojciech Zurek, Murray Gell-Mann, Jim Hartle, and other physicists who used the decoherence phenomena to build models of macroscopic universes emerging from the microscopic realm without resorting to the sort of non-physical idealizations that Everett himself eschewed, such as Wigner's theory that human consciousness rules the quantum reality, or theories that attempt to causally separate the mind from the body. But the basic premise of modern Everettianism, to coin a new ism, is that all that is governed by quantum mechanics. Zurek sums up the abiding legacy of the many worlds interpretation. It was Everett who gave us permission to think about the universe as wholly quantum mechanical. But saying such a thing in the 1950s was downright heretical, since the collapse postulate and the Copenhagen interpretation ruled the foundations of quantum mechanics. Bohr, Bohr had written in biblical stone that we should not even ask what goes on inside the quantum world, since acts of observation must remain forever external to it. Everett's legacy was to show that models of the quantum world can be constructed from the point of view of an observer inside that world, herself a superposed quantum object. In recent years, experimentalists have created and observed superpositions in the lab, so who knows where this will lead. There are two published versions of Everett's theory, a 136-page dissertation that he turned into his thesis advisor, John Wheeler, in January 1956, and a severely edited and rewritten version that became his final PhD thesis, and which was published in Reviews of Modern Physics in July 1957 in a special section edited by DeWitt, who remained Everett's champion until he died just a few years ago. To shorten the story, Wheeler refused to grant Everett his degree until he had toned down talk of splitting observers and bifurcating universes in his draft thesis, as well as his overt criticisms of Bohr. Everett complied, albeit unwillingly, and he believed that the thundering silence with which the publication of his dissertation was met in 1957 was the direct result of Wheeler forcing him to cut 3/4 of it, much of it explanatory in terms of mathematics and interpretive language. In public, Wheeler flip-flopped on Everett's theory for years, sometimes championing it, sometimes disparaging it. But after Everett's thesis was curtly dismissed by Bohr and most of the physics establishment, including Wheeler's star student Richard Feynman, Everett never wrote another word of theoretical physics, and Wheeler ultimately completely disassociated himself from the theory. Leaving Princeton, Everett took a job with the Weapons Systems Evaluation Group at the Pentagon doing top-secret military research. His first task was to calculate kill ratios for the distribution of radioactive fallout from nuclear conflagrations. A declassified version of this work was made public in 1959, and 3 years later, in his speech accepting the Nobel Peace Prize, Linus Pauling applauded Everett by name for determining that fallout from even a small nuclear exchange would destroy most life on Earth. Everett himself was no peace activist, far from it. He kept himself busy designing encryption software for the National Security Agency and inventing nuclear war simulation programs on supercomputers. As the chief mathematician at the Weapons Systems Evaluation Group, he was instrumental in creating Report 50, a top-secret investigation detailing the broken state of the U.S. military's offensive capabilities in a nuclear war. The classified report convinced President John Kennedy and his Secretary of Defense, Robert McNamara, to try and steer the nuclear war plan away from its massive first strike mode, known informally as wargasm, to a more flexible mode of attack, based upon launching a triad of bombers, submarines, and intercontinental ballistic missiles bearing nuclear warheads. Report 50 institutionalized the concept of mutual assured destruction, also known as MAD. In the early 60s, Everett led the computational team that designed the nuclear war targeting program for MAD, called the Strategic Integrated Operating Plan, which turned out to be not very flexible, nor integrated, or strategic. Due primarily to political considerations, it entertained 5 basic attack modes, all of which pulverized the socialist bloc and poisoned the rest of the world with radioactive fallout, followed by nuclear winter. It is strange to think of Everett designing weapon systems that he believed were destined to destroy his personal world and universes beyond number. In 1959, Everett and his young family traveled to Copenhagen and spent several weeks vacationing. Mixing business with pleasure, Everett met with Bohr several times to discuss his theory, but the two men were on opposite sides of the wave function in terms of how they viewed quantum mechanics. Bohr smoked his pipe and mumbled obscurely in their meetings, as was his trademark behavior in his old age. Everett spent a good deal of time bar hopping. And in the bar of the Hotel Osterport, after imbibing a few beers, he invented and wrote down on hotel stationery what became known as the Everett algorithm, also called the Generalized Lagrange Multiplier. A creation of the information age, Everett's Magic Multiplier method solves complex nonlinear optimization problems with sampling techniques. It enables the calculation of ranges of consequences or prices for making real-world decisions to expend specific amounts of a resource to overcome a constraint. Problems of this type include maximizing the efficiency of assigning targets to hydrogen bombs, scheduling just-in-time manufacturing runs, allocating bus routes to most efficiently desegregate school systems, and projecting the political fallout from funding specific foreign and domestic policies. The Magic Multiplier was a cornerstone of Everett's career at the Pentagon and after 1964 at his private think tank, Lambda Corporation, where he continued working for the National Security Administration Agency on cryptographic programs. He also designed computerized war games for the Joint Chiefs of Staff as well as anti-ballistic missile systems, none of which work since they are easy to overcome. He invented compression algorithms for the first generation of relational databases. His clever algorithms categorized and tagged information for retrieval without having to search the entire memory mechanism. His path-breaking work in cybernetics made him comfortable, but he never became wealthy because his business skills were lacking. Other men got rich utilizing his inventions, but that is another story. In 1962, Everett was invited to explain his quantum theory to a panel of stellar physicists convened at Xavier University in Cincinnati, Ohio, to ruminate on the seemingly intractable measurement problem. A transcript of that proceeding was made public 40 years later. It is a fascinating document showing an intimate, sometimes angry colloquy between scientific heavyweights, including Eugene Wigner, Paul Dirac, Yakir Aronov, Wendell Furry, Boris Podolsky, and Nathan Rosen. So desperate had these thinkers become to solve the paradox of measurement that they were willing to entertain the idea of multiple universes if it provided a way forward. Everett despised public speaking, but he could hardly have dreamed up a smarter, more informed group of physicists to address. It was the first of only 2 known occasions in which he explained his theory to a gathering of his peers. In response to a question about the reality of the branching universes, he said, "Each individual branch looks like a perfectly respectable world where definite things have happened." And he agreed with Podolsky's comment that the worlds are uncountably infinite. No one present cared to dispute Everett's logic, but neither were they eager to accept it. Furry, who is pictured here, remarked, "For me, the hard thing about it is that one must picture the world, oneself, and everybody else as consisting not in just a countable number of copies, but somehow or another in an unenumerable number of copies, and this my imagination balks. I can think of various alternative theories doing different things, but I cannot think of a non-denumerable number of alternative theories." The meeting adjourned without solving the reason for its inception. But a half-decade later, in 1967, Bryce DeWitt was looking to develop a theory of quantum gravity. He turned to Everett's universal wave function because it allows the universe to be described by an observer inside the universe, inside a wave function theoretically capable of containing all quantum mechanical and gravitational processes. In a series of academic papers and magazine articles, he popularized Everett's work, and in 1973, Princeton University Press published Everett's original unexpurgated dissertation. The volume's editors, DeWitt and his student Neil Graham, renamed it the Many Worlds Theory, and it caught on, inspiring several generations of physicists working on quantum gravity, cosmology, and string theory. In 1977, Wheeler and DeWitt invited Everett to give a talk at the University of Texas in Austin. Dressed in his customary black suit, he chain-smoked while pacing and speaking in a rapid-fire staccato. According to the physicist David Deutsch, who was there, Everett spoke of the many worlds as if they were physically, ontologically real. Sadly, the gradual acceptance of the revolutionary theory as a possibly viable interpretation of the quantum world came about largely after the untimely death of the theorist, as his personal world was collapsing. At the time of his demise in 1982, Everett's consulting firm was disintegrating due to cutbacks in military research budgets and his mismanagement of the business end. He was ruined financially and personally, his body racked by compulsive smoking, drinking, and eating. His marriage had long been troubled, and his self-effacing wife, Nancy, was resigned to accepting his multiple affairs with employees and prostitutes while engaging in a few sad affairs of her own. Only Nancy knew of the black depression that fueled her husband's alcoholic self-destruction, and she felt powerless to intervene. Here he is making homemade wine in the kitchen, which is the cleanest room in the house. Ironically, Everett had devoted his life to making models of reality, but he was largely oblivious to the harm he caused those closest to him. He barely acknowledged the existence of his troubled children, Mark and Liz, who yearned for parental attention. When Everett died suddenly of the heart attack, his teenage son, Mark, trying to revive his corpse, reflected that he could not ever recall having touched his father before in life. After his father died in 1982, Mark moved to Los Angeles and became a successful songwriter, known to his fans as E, of the band Eagles. Liz committed suicide in 1996, leaving behind a note saying that she was going to join her father in another universe. 2 years later, Nancy died of lung cancer, probably from her husband's secondhand tobacco smoke. In June 2007, Mark and I descended into the basement of his house in the hills of Los Angeles. One wall was lined with wooden shelves holding the family saga, 24 cardboard boxes bursting with memorabilia and paper trails. We opened up his father's boxes for the first time since they'd been packed a quarter century previous. They held old textbooks, physics and operations research papers, stacks of letters, used airplane tickets, canceled checks to liquor stores, stained hotel receipts, a Super 8 porno film, and a scrap of paper on which the physicist had scrawled a fallacious proof of the existence of God in the predicate calculus. Several boxes were stuffed with thousands of sheets of yellow legal paper covered with algorithms variously designed to track ballistic missiles with nuclear warheads or outwit the housing and stock markets. Another box held artwork made by the kids for Father's Day. Laying beneath the childish art were letters from some of the most renowned quantum physicists and philosophers of the day: John Wheeler, Norbert Wiener, Philip Frank, Niels Bohr, Henry Margenau. Chief among the finds was the original handwritten draft of Everett's dissertation. In a short paper excerpted above there, in which he compared his splitting universes to splitting amoebas. Okay, biologists, I threw that in for you. At Wheeler's urging, the amoebas did not appear in his final thesis. Sorry. Indeed, Wheeler had insisted that he remove all references to splitting, including amoebas especially, although Everett rebelliously sneaked the split word into a footnote added to a galley of the Reviews of Modern Physics version before it went to print and unknown to Wheeler. And even though Everett never wrote another word of quantum theory, letters among his effects show that he had followed the rehabilitation of his theory with great interest. Though galled by what he perceived as the failure of his intellectual peers, including John Bell, sorry, this is messed up here, and DeWitt, to understand the derivation of his probability measure at the core of his theory. Next to DeWitt's critique, he scrawled, "God damn it, you don't see it." The good news is the basement measures illuminate Everett's thought processes, and that is a contribution to the history of science. In 2010, Oxford University Press published my biography of Everett, which I like the deck, Multiple Universes, Mutual Assured Destruction, and the Meltdown of a Nuclear Family. It's hard to memorize, though. Sorry, Greg. And then last year, Princeton University Press published the collected works of Everett, edited by myself and Jeffrey Barrett, who's a professor of logic and philosophy of science and actually can do mathematics, unlike yours, truthfully, and at UC Irvine. And then the National Science Foundation funded us to put all of Everett's scientific papers online, which they are at UC Irvine. It's a very nice collection. And then it turns out that Germans like Everett, too. And I have to tell you, when they put it together, it was a few years ago, so at my request, the mushroom cloud emanates from Wasilla, Alaska. But now, let us hear from the man himself. The tape recording I'm about to play was made at a cocktail party in 1977. In it, Everett talks with his lifelong friend, his college roommate, renowned physicist Charles Misner, about what inspired him to think about weird quantum mechanics.
Testing, 1, 2, 3, 4, 5. Testing. Come down here. Okay, great. Well, it's been a great evening. I enjoyed spending our 18th anniversary with you, Hugh. And why don't you lead on after your drink by telling us how you got started with John Weir. What I heard made you decide to pick him for a thesis about it?
Well, actually, I didn't. Somebody assigned him to me. And I needed one to get my fellowship renewed.
So it was all bureaucracy.
That's correct. First year was actually spent in the mathematics department.
Now, when did you get on to weird quantum mechanics?
Oh, it was because of you and Owen Peterson one night at the graduate college after a slosh or two of sherry, if you might recall. You and I were starting to say some ridiculous things about the implications of quantum mechanics. And I was having a little fun joshing you and telling you some of the outrageous implications of what you said. And, once we had a little more sherry and got a little finer in conversation. Don't you remember, Charlie? You were there.
I don't remember that evening, actually. Peterson was around. That's entirely
You made too much sherry.
Yeah.
That's it. Thanks. So entertain questions.
Okay, so let's take some questions. If there are any.
If I preempted the questions and actually got through 61 slides, is that a record at KITP?
Well, usually we interrupt speakers, but was there?
Yes, as a non-quantum mechanician, how does splitting the universe differ from collapsing a wave function? In both cases, you're going from a linear continuous evolution to something that's discrete and discontinuous. And so don't you have the same quantum decoherence problem when you split a universe that you have when you have Copenhagen quantum decoherence?
Yeah, you do, but your copies, and so do your copies. But the idea is that in reality, the universe at large, the wave function is never collapsing.
But it doesn't address why the observation causes the split.
Well, true, it doesn't. But I think that what Everett was getting at in his dissertation was primarily a mathematical construct, which, as we all know, doesn't have to necessarily accord to physical reality. And it's often misconstrued that the universe splits every time there's a quantum interaction. That's not what Everett was saying. You know, I mean, basically, he used the example. He had gone to went to Einstein's last lecture at Princeton in 1954, I think it was, in which Einstein said something like, you know, he didn't believe that the quantum mechanical universe depended on the perception by a mouse. And Everett remarked in one of his papers later that it wasn't the universe that split, it was the mouse that split, you know. So it's a series of what he called relative states, which is actually much more functional than many worlds, you know, in terms of describing what he was getting at. That in every quantum interaction, that there's a correlation. The observer splits to correlate with every element in the superposition, and you know this is of course going on in multiplicity of directions and you know all that. So the idea was highly abstract, really. Although, you know, some people consider Everett's wave function to be real, Everett was actually an empiricist, and therefore did not actually ever say that he thought that his worlds were real. And the closest he ever came to saying anything was he told one of his friends once that he was 70% sure that maybe they were real. But, you know, basically, Jeff and I analyzed it as, you know, when we talk about Everett believing his theory was empirically faithful, which is a much weaker criteria than being empirically adequate. And it was empirically faithful because it describes the world as you see it. Well, so do a lot of things, right? You know. And Everett actually, you know, he was not just into game theory. He actually wrote one of the most cited, important game theory papers of all time. It was right up there with Nash. And unfortunately, he played games in his life constantly. You know, he wasn't really a nice guy. And I really believe that at a fundamental level, he just thought this was a pretty funny dissertation to write, and he would have been absolutely shocked by what's happened with it, But a lot of people take it really seriously.
Yes, David.
Is there any prediction he made or people made with this theory that can be tested, falsified?
It can be falsified?
I mean, that's the idea of physical theory.
No, his theory can't be falsified.
Sorry?
No, his theory cannot be falsified.
So it's not a scientific hypothesis.
It's
a scientific hypothesis has to be falsifiable.
Well, that's what Karl Popper says. There's people that would disagree with that.
Well, they're wrong. Karl Popper figured out what science was about.
I'm not advocating one way or the other for Everett's theory, because I do not know. However, it certainly has been criticized on that, and also on Occam's razor grounds, and others. People have actually, especially the people at Oxford, have gone to great lengths to address those types of issues in very long, jargon-filled
people
papers.
At Oxford in which department?
Philosophy of science, yeah, and elsewhere. But the remarkable thing to me is that it keeps stirring up all this talk, after all these years. And
because of the science fiction.
Well, some people consider, science fiction people really like it, but physicists and philosophers like it. That's just a fact.
This term, I have a question. This term, consistent histories, does that originate with Everett?
No. That's Jim Hartle and what, David?
Griffith.
And Griffith, yeah. I didn't mention his collaborators because I was running out of breath, but it was Griffith and Omnes and right. Yeah, they have.
Anyway, but that's they describe a consistent way of just talking about physical reality. This is not science, and it's more philosophy of science.
Mm-hmm. Well,
because,
as
you say, he didn't accept these things as real.
Yeah, he didn't.
Whatever real means. But physics usually means something that has some causal connection with it. This is a way of describing it, as opposed to Wavefunction, which is equally funny. But it isn't like a physical theory.
Well, interestingly enough, when Hartle and the rest of them, Gelman and all, were putting together a consistent histories approach, they credited Everett as inspiring them, and their program was to complete what he had done.
Who was also inspired a lot of people too.
Mm-hmm.
Bad idea, I mean, you don't have inspiration. Requires a lot less than success in physical theory.
True, and there really need to be criteria by which we judge it.
Inspire. And indeed, he was one of the first to address questions of quantum mechanics historically, which were sort of off the books.
Mm-hmm.
So supposed to do this.
Well, kind of like Zurich's summation. I mean, Zurich doesn't go around saying the worlds are real or not. He says he gave us permission to think about the world wholly quantum.
What do you mean he gave us permission?
That's what he said.
Stimulate people like many people did to try to go back after not only 20 years but 30 years after quantum mechanics was founded, and look at it again. Generations do, and try to understand. Clean up some of the original interpretations or original descriptions of what quantum mechanics is, and with enormous progress. So it's true, he was a pioneer in that sense, but it doesn't lend credibility to the existence of many worlds. The reason it's had so much popularity is, in fact, the science fiction aspect of it, in my opinion. The fact that you talk about many worlds, even uncountable many worlds, uncountable to the uncountable power, an uncountable number of points in this room, and each has, if X is the splitting measurement. It's an uncountable number of universes to an uncountable power. That boggles the mind if you start thinking of them as universes with people in them doing their thing. Well, the way from the beginning people start talking about it.
Well, people have been talking about multiple universes since before the Greeks. You know? It goes way back, and you wouldn't believe the letters I get from people saying, well, since everything is possible, there must be a God. Which is actually that when he wrote number of gods. Oh, that's really scary. But that fallacious ontological argument he wrote down was actually an argument against that. So he must have been getting. I remember now. He was getting some flack from people, that were. Charlie Misner, for one, actually, about that. Was there a question that somebody...
Yeah, in the back?
No, unrelated question to the multiverse. You said that he invented Lagrange multiplier to solve problems. I was surprised. I'm sure that people were using that much before.
Generalized Lagrange multiplier. And it was for computers. Obviously
to solve problems with constraint. That's how.
There wasn't enough information given to figure out what the claim was there exactly. But
if you Google it, you'll come into a wealth of information about it.
Certainly an entire field about constrained optimization, which is very well developed. Now the question, I don't know.
Well, he was an
pioneer of that. But.
He was in operations research, and he did pioneering work in game theory, operations research. Like I said, relational databases.
Has it been published, or is it?
Yeah, a lot of it's been published. Yeah.
So what's
the Lagrange?
Google?
Pardon?
What term should I Google to try to get that?
Just try generalized Lagrange multiplier, or probably Everett multiplier, or buy my book.
Google buy your book.
In multiple universes.
Question in the back?
I sold 80 billion copies so far.
Yeah.
There's nobody behind me.
No. Well, the ones which natural laws apply.
No, go ahead. There's a question.
I was wondering whether the multiverse theory that emerged in cosmology, whether it has anything to do with the many.
Oh, you mean like the landscape and stuff like that?
The answer is probably no.
What?
So the next question is whether it's contributing to some extent in legitimizing Everett's.
Well, if you talk to, as I have, people that are promoting those ideas, they will actually say that Everett was basically right or partly right or inspired them to look in this direction.
Susskind would say that?
Yeah. Okay. He would say that there's that the landscape should be looked at in terms of universal wave function a la Everett.
Well, the great success of Everett's many worlds has given motivation
to the landscape
to be able, given permission to invent other unobservable.
Yeah, question here.
No, it was published in Operations Research, 1963, volume 11, and cited more than 1,000 times in Operations Research.
What's
in one universe?
Generalized Lagrange multiplier method of nonlinear optimization.
I see. Okay. Yes.
So I don't know if it is a question or comment. Max Tegmark has an article in Scientific American which he talked about 4 levels of parallel universe.
Right. Yeah, 2003.
So I think the landscape is level 2 and Everett is level 3.
What depends on who you talk to.
I'm sorry, what was level?
So level. Yeah. So level 1 is that you have a limit as to how far you can observe about your local universe, and so there are places where the physics law is where the effective physics law is the same, but you cannot observe. That's level 1. And level 2 is that you have this. I think in the modern language, it says string theory has many metastable states, and so you can have places with different fundamental constant and all that, and that disconnect. That's level 2. And then level 3 is this quantum mechanics splitting of multiverse. And then there is a mysterious level 4.
Well, you'd be surprised who out there really says that the worlds are real. I mean, Alan Guth said that. I interviewed Juan Maldaceno, and he said, when when I just think about it philosophically, I don't believe it. But when I do it quantum mechanics, I do. I mean, there's plenty of people out there that actually think that this is an accurate ontological approach. Now, I will add that I'm in the process of doing a screenplay on this with a Hollywood director. Talk about throwing science out the window. When I approached it, our first draft was like pretty, I explained like I did today from my point of view, But now it's like this love story with lots of nuclear bombs going off. It's really interesting.
Who will play Hugh Everett?
Well, I'd like to get Kevin Spacey, but.
Okay, yes.
This comment was more relevant a few comments ago, but anyway, I'll still give it. I went to Brian Greene's talk the other night, and he talked about multiverse, obviously. And my second favorite moment was in response to a woman who asked something like, okay, so if everything's expanding, so like as I get older, I'm expanding. Is there like another universe where, I don't know, I'm either young or skinny or whatever, I don't know, something like that. And he said, oh, how I love California.
Well, first of all, it has to be physically possible, so maybe some things are and some things aren't. Second of all, Brian is like Mr. Multiple Universe these days, and he gave me some nice footnotes in his book.
But your observation is maybe this theory is particular to California in some way. If Everett lived in another state or something.
Those kind of questions.
Well, he formulated this in New Jersey, though.
Yeah, Princeton.
Yeah.
It sounds like Brian was dodging the issue, actually. But if you want to reformulate it, I try to answer it. I mean, it does have to be physically possible, whatever that means. I mean, there's probably no universe where I am a string theorist, But it does bring up an interesting question, like David was alluding to as well, which is, why do people want to believe in this? I mean, don't we have enough problems in our own world? So why do we want to have this very convenient construct where all those problems get solved? Only, and the Everettian philosophers take this to an extreme. They've invented concepts of quantum suicide.
So there was a 1980s, the first time I was at the ITP, organizing a workshop in 1986. There was Murray Gell-Mann was around, and we had a blackboard lunch on foundations of quantum mechanics. Because at that time he was working with Gen 1 in their histories. And and as is often the case, many worlds came up. And Murray expressed his opinion that this was nonsense, and he offered to bet with anyone in the audience. I think you're coming to this. But what he offered was a bet with anyone in the audience to play Russian roulette, and he would offer them $1 million, or maybe it was like $500,000 per bullet. But the idea was that if they truly believed in the many worlds, which are uncountably infinite, splitting at each time, there's a very good chance that they're going to survive in an uncountably infinite number of worlds. Any probability times infinity is infinity. So, and in that world, if they survive, they'll get $1 million.
Yeah.
They don't.
Hopefully nobody's taken anybody up on that.
No, but he has to survive too.
But, I mean...
and it really shows, by the way, that nobody believes a word of this.
Well, the philosophers get really tweaked out of this whole thing, because then they start going off on well, if everything's possible that happens, do I have a moral responsibility to my other copies? Seriously, they write whole papers about this.
I think David Gross's comment that inspiration comes from many sources, some which we can't track and some which we can. For instance, an analogy with the word teleportation, which is now used in quantum information science, since Charles Bennett introduced it as a term, quantum teleportation. You could say, well, that started because of Star Trek. In the 1960s, you had a teleporter. And, complete science fiction. they weren't thinking of any actual physical theory then, I don't think. But the term, maybe this inspired people subliminally. Maybe only the term survived.
It inspired Charlie Bennett to come up with a good title.
Yeah, exactly.
Get attention for your work.
Right.
It used to be called moving.
So, I mean, this could be
actually what I did find
analogy to what's
well, I mean,
happening.
it's one thing to talk about this to a room full of scientists, and it's another to talk about it to a room full of non-scientists, because this sort of thing for me and for a lot of other people is the only way we can really get into this type of science, because we're not wired to do the calculations, which is fine with me. I don't want to, but it's really but you have to be careful because it's a minefield. Because you can come up with the most outrageous bullshit, and shouldn't believe everything that looks attractive either. But it is interesting. I mean, to write this book, I had to read like 150 papers in quantum mechanics, and I read around the equations, and I read books, and I learned a whole lot. It was great, and I get a lot of pleasure out of passing that on to other people, without mystifying it.
I think some people may correct some of your equations because there are a few errors. So I'll let them do that.
Feel free to.
Let's thank Peter for his entertaining talk.